Hello, everyone. My name is Baram Jalali from the Jalali-Lab at UCLA, and I have the pleasure to speak to you today about physics-AI symbiosis, how to utilize physics to enhance AI and vice versa. My co-authors are Professors Kadampi and Richard Huri, distinguished faculty members and colleagues at the ECE department at UCLA. This talk is organized as follows. I will provide a historical perspective. This is a personal and somewhat subjective view on where we are and where we might be heading. Then we will discuss the limitations of the current approach of AI, and in particular, the issues posed by the Moore's law of semiconductor scaling and also by the Shannon information theory. We will then talk about the main aspect of this presentation, the physics-AI symbiosis. The topic is divided here into 4 pillars. The first pillar is AI replacing physics, so to speak, with lots of help from physics. Pillar 2 describes the ideas that could be categorized as physics intermingling with AI. Pillar 3 is physical hardware blending with AI. And pillar 4 is physics designing algorithms, a new approach to algorithm development, which is guided by physical laws. And then I will make some concluding remarks. So physics and AI are 2 extremely different approaches to modeling a system based on the data that we have about that system. In the early days of science, before we had instruments to measure things accurately and mathematical tools to model them, science was empirical. As empirical laws were formed by trial and error, and the laws were a mixture of reality and also superstition. For example, all sailors believe that if you set sail on a Friday, you will never return, you will be lost at sea. So no ship would start its journey on a Friday. So these were superstition and empirical laws based on some data, but obviously incomplete data. In the past couple of centuries, we invented great instruments for measuring things with high accuracy, and we developed mathematical tools to model that data using first principles. And this was the age of physics. So science evolved from empirical to being deterministic. Now, thanks to the semiconductor industry, in the last couple of decades, there has been an exponential rise in our ability to collect data and store that data and to perform computations on it. So this has led to the rise of neural networks as the universal model, which given enough data and enough compute power, they can fit any data and extract subtle information from them. Now, while neural networks have been spectacularly successful, especially in image classification and speech recognition and synthesis, there is now growing conviction that the next chapter will see a hybrid approach where the laws of physics and physical systems merge with AI, or vice versa, depending on where you start with. It is anticipated that this symbiosis of physics and AI will be of mutual benefit to both, and will also pave the path to applications not possible with each of them alone. Now, an early example of how physics and data-driven approaches can work together was the Apollo mission's navigation system. In the 60s and 70s, computers were very crude, and sensors consisted of manual observations using a sextant, a device from the age of sailing ships. But with the lives of astronauts at stake, neither the physics-based calculations performed on these primitive computers for the trajectory, nor the sensor data alone could be relied for accurate navigation. So the Apollo navigation system made use of the Kalman filter, in which both a physics model and measurement, the data, are used to make the necessary predictions about the trajectory. So Kalman filter can be considered as an early example of how blending physical and data-driven techniques can solve important problems in situations where computational power is limited or the data is limited and noisy. With that historical perspective out of the way, the next section in this talk will highlight some of the limitations of the current deep learning approach to AI. And these are limitations that are related to Moore's law and to the Shannon information theory. So neural networks are black box models with a large number of free parameters that can be adjusted to fit essentially any pattern in data. The modern deep learning networks have over 1 billion adjustable parameters or nodes or weights. And this is precisely why they're so successful. In the training phase, a large data set of known input-output pairs are presented to the network, and these weights are adjusted by minimizing the error between the predicted output and the known output using the backpropagation algorithm. In the inference stage, the stored weights are used to make predictions about the output given a input that's different than the one in the training set. In image classification and speech recognition, these things have even outperformed the humans. So indeed, very, very successful. At the same time, there are problems that are arising that question whether the current breakneck rate of progress can actually be maintained. And there's a consensus that judicious use of both natural laws, physical laws, and neural networks can lead to new types of AI and enable new applications not possible with each of them alone. Now, so in the next section, we'll talk about these limitations, and then we'll talk about the 4 pillars of AI. So some of the limitations with AI are well known and well documented. These include the lack of generalization outside of training data set and the lack of interpretability. So the two that I like to emphasize here, the first one is that the semiconductor technology cannot keep pace with the increasing demand for compute and memory by deep learning networks. And the second issue is that the Shannon information theory says what it says about what kind of data you need to make accurate inference in cases that matter most. So the use of GPUs and ASICs in deep learning has fueled a lot of the spectacular success that we've seen. However, while GPU power continues to increase, the rate is fundamentally limited by the Moore's law. That's the black line here, which is indeed exponential, the y-axis here being in the log scale. However, the compute demand of neural networks, shown by this red curve here, has completely outpaced the Moore's law. And so the semiconductor technology by itself will not be able to keep delivering the needed compute power under the current trajectory. And introduction of the physical laws can potentially help here. Neural networks learn information from data, and so they need large data sets to be trained, to train their billions of weights and so forth. However, as Shannon tells us, it's not the data that matters, but it's the information in the data. So it's useful to remind ourselves that data is not necessarily information. So Shannon's information theory tells us that the amount of information as quantified by the entropy is inversely proportional to the probability of occurrence of a particular event. So the more rare an event is, the higher is its information content. A typical classification problem, say detecting a cancer cell or detecting an impeding crash in a car, is asymmetric. Like a needle in a haystack, there are a lot more of normal events than there were events of interest. Now, in many applications, we don't have large enough data sets in which there are enough examples of the rare event. So these rare events cannot be accurately inferred by the neural network because the network never saw examples or enough examples of those rare events. So we could say that the neural network will fail when it matters the most. These rare events are also called corner cases. Now, in some application domains, such as detecting a cancer cell from medical images or in self-driving cars, these missing corners or rare events can be fatal. So bringing physical knowledge and physical constraints into AI can potentially help with this issue as well. Now, the third problem with the current trajectory of AI is the latency, especially in deep learning networks. Low latency is required when classification must be made within a feedback or feed-forward control loop. One example which we have been faced with or working with in our lab has to do with the classification of cancer cells via image-guided cytometry. Here, blood cells flow at high speed, and they are imaged using an ultra-fast time stretch camera invented in our lab in the late 2000s. The microscope takes line scan images of these cells as they flow using a femtosecond pulses. The shutter speed is very fast, so there is no image blurring going on. These image frames are then subsequently slowed down using photonic time stretch, so they can be digitized and stored for further processing. A deep learning network then classifies these images. And in order to sort the cells downstream into the particular subpopulation, the classification must be done in a few milliseconds. So a recent work from our lab demonstrated that one can perform these kind of diagnostics using time stretch microscope with deep learning, and one can reduce the latency of the deep learning in the inference stage to below a millisecond, which is sufficient for cell sorting downstream of the image capture. Now, combining AI with physics to solve these problems has become an active topic of research, rich with many innovative ideas. For the purpose of this talk, we will categorize the various approaches into four categories or four pillars. And in the interest of time, I can only provide a flavor of what the basic ideas are. So realistic simulations of complex physics are valuable to scientific research, to engineering design, but also they have applications in animation for movies and video games. But high quality simulations require substantial computational resources, which make them difficult to scale up. For example, in hydrodynamic simulations, the computations are quite intensive, and doing say animation, providing real-time animation is quite prohibitive. Now, AI models can be used as replacement or surrogates to first principle physics models. The idea here is to use the physics simulators to generate training data, then train a neural network and use it for forward simulations under different conditions. So the physics simulations are only done once in the beginning. And while training of neural networks is computationally heavy and could take a long time, the training has to be done only once. In the inference mode, these models are much faster than the first principle physics models. Now, another approach that fits under the same category is to use a neural network not to make final predictions, but rather to learn a partial differential equation or the components of a partial differential equation that govern the actual physics. The second example in this pillar is inverse problems, using neural networks to solve inverse problems. Now, a canonical example of inverse problem is the phase retrieval problem, retrieving the optical phase from measurements of the optical intensity alone. This is an ill-posed problem, very well known, and is particularly hard. Now, here I'd like to show an example of using AI for phase retrieval of femtosecond pulses in spectral interferometry. This is a technique that has a wide range of applications, is used for characterizing ultra-short pulses, in study of the dynamics of solitary molecules, in performing real-time vibrometry and velocimetry, and also spectral interferometry is the basis for the phase contrast time stretch microscope developed in our laboratory for label-free classification of cancer cells in blood. Now, here is an example of what neural networks can do. This is, again, an inverse problem in which neural network is being used to recover the phase and amplitude of femtosecond pulses in spectral interferometry. Now, this work introduced two innovations. One is, how do we generate training labeled data sets when our data consists of femtosecond pulses? So here, the example of training data set phase amplitude profiles were generated digitally and were modulated onto the spectrum of femtosecond laser pulses using a spectral interferometer in a wave shaper. Now, the problem here is that while we can generate arbitrary phase and amplitude profiles digitally, how do we ensure consistency with actual physics? In particular, how do we ensure that these profiles follow causality? So to make these training pulse profiles causal, we subject them to the chemical-chronic relationship in the digital domain, and then they're subjected introduced to the spectral modulator. The second innovation is, how do we read the interferogram of these femtosecond pulses in single shot in real time with high sensitivity? And for that, we make use of Raman amplified time stretch technology that was created in our lab in the mid-2000s for real-time single-shot readout. So this is the front end of the system. The back end of the system is shown here. And after the single-shot spectra are captured using an amplified time stretch, they're introduced to a 5-layer neural network. And the output of the neural network produces a single vector, which is a concatenation of the magnitude profile and the phase spectral profiles. Here, we compare the performance of the AI phase retrieval and amplitude retrieval compared to Hilbert transform. Now, Hilbert transform is currently the gold standard for retrieval of amplitude and phase from spectral interferograms. So here on the top row, we're showing the performance of the Hilbert transform. The red curves are the magnitude and phase profiles, ground truth, and then the blue are the retrieved magnitude and phase retrieved by the Hilbert transform. The bottom two rows are the performance of a neural network. The top row was trained with a small experimentally trained generated data set, 225 pulse profiles, and the bottom one with a large set, 5,400 pulse profiles. And as we can see, the neural networks perform much better than Hilbert transform. The blue curve, the experimentally measured profiles, are in much better agreement with the red, with the ground truth. And even this is so even for a small data set. Now, another point to be made here is that the Hilbert transforms, these were not single shot. They could only be obtained by averaging over multiple pulses, whereas the AI performance is under single shot conditions. Further details about this work appears in the conference on AI and applied data sciences here at Photonics West. Now in pillar 2, we talk about approaches that could be categorized as physics intermingling with AI. Now, there are many interesting approaches being pursued here. Some of them can be categorized as data augmentation, physics regularization. I'll show you examples of these two. Physics-guided initialization, in which the network is initialized by training by a physics model, and then the model weights are fine-tuned by retraining with experimental data set. And this could also be called the type of transfer learning. And then other examples include physics residual learning, and then physics boundary conditions. Now, in the data augmentation, we have a data set that is normally used to train a neural network. Now, in many cases, the data set is not large enough, or the neural network will have to be quite deep in order for the initial layers to perform the necessary feature extraction and so forth. Now, one thing that could be done to alleviate that problem is to send the data to a physics model. The physics model would act as a feature extractor, and these extracted features are then combined with the initial data and sent to the neural network. And the idea here is that the network does not have to be as large, does not have to have as many layers and as many weights in order to recover patterns in the data once these features are also produced at the input. Another example is physics regularization. Now, in this case, the loss function that is optimized, which normally consists of the basic loss function comparison of the ground truth with the predicted output, and then the conventional regularizer, the ridge regression regularizer. Now, in this case, one adds another regularization term, which applies the constraints imposed by the physics as an additional term in the loss function that guides the optimizer towards solutions that are consistent with the physical laws. Now, this is a very fast-moving field, and already there are commercial tools developed to implement these kind of ideas. This is NVIDIA's AI Accelerated Physics Simulation Toolkit, which allows the user to create parameterized models of the actual physics models for fast simulations. The pillar 3 in the symbiotic relationship between physics and AI is when physical hardware and AI start to merge. This approach requires optics that can be reconfigured and trained via the algorithm. Optical implementation of neural networks is an idea that has seen a resurgence lately. This approach employs free space Fourier optics to create computing accelerators. These are massively parallel ways to process lots of data. This particular example is a recent work from the Sorger group at the GW University. And in this work, the group reports a processor, a Fourier optics processor that works with amplitude only. And this amplitude-only operation is robust against noise associated with phase fluctuations. The processor performs convolutions as pixel-wise multiplications in the Fourier domain. and they demonstrated classification task on 2 megapixel images on the MNIST database and more. So the convergence of physical hardware such as this with AI requires optics that is reconfigurable. Now, in this example, they use digital micromirrors or DMDs, and other groups employ liquid crystal spatial light modulators. Next, I'd like to show a couple of examples of digitally reconfigurable optics developed in my laboratory that lend themselves to computational sensing and imaging. The first one is a new type of fluorescent camera we developed a few years ago that's capable of record shutter speed and frame rate. The fluorescent sample is illuminated with a radio frequency modulated optical shower. The laser beam is shaped such that different parts of the laser beam have different amplitude modulations. For example, this part is modulated with 100 megahertz, 101, 102, and up to 256 unique radio frequencies. When the fluorescent molecule emits, the emission is tagged with the same radio frequency. So based on the radio frequency spectrum at the receiver, one can create an image without a pixelated camera. And because it eliminates the camera, it eliminates the readouts time, and therefore it can achieve record speed. Now, this is particularly suited for blood sorting and has been quite successful in doing so. But the key here is that such a hardware is digitally reconfigurable and can be tailored for a particular task. This is the hardware for achieving that kind of illumination. We're not going to go into details, but basically it uses acoustic deflectors driven by frequency comb, RF frequency comb, to create that spectrally modulated RF shower onto the sample. And because of its extreme speed, it's quite suitable for imaging blood cells during high-speed flow for fluorescent-based flow cytometry and cell sorting. Now, the second reconfigurable hardware is a discrete implementation of the time stretch imaging. In this case, the sample is illuminated not by a radio frequency comb, but rather by a multi-wavelength comb. And also, because the illumination is pulsed, then the beam can be amplified to deliver high energy to each pixel and stimulate multi-photon emission. Now, these pulses are temporally sequenced, so the image decoding at the receiver can be done simply by looking at the timestamp of the arrived signal. Also, by looking at the decay of each pulse, the system can capture fluorescent lifetime images. The key point here, again, is that this illumination pattern is digitally set so that it can adapt and optimize to a specific task. These are examples of the two-photon fluorescent images and two-photon fluorescent lifetime images captured in that camera for two particular samples. Now, the same system, because it can deliver high energies to each pixel, can be used to realize a LiDAR. And here, once again, the target is illuminated with multi-wavelength temporally sequenced or temporally stretched pulses. And the receiver, by looking at the time stamp of the received signal, one can create an image which has the range information, so 3D ranging camera. And because it eliminates many of the bottlenecks in conventional LiDAR, this LiDAR has actually achieved record frame rate. Now, the key point here again is that the illumination pattern is digitally controlled, so it can be tailored for the particular image. So these are point cloud results shown for different illumination patterns which are digitally set, uniform illumination and then foveated illumination where pixel density is allocated to different parts of the image of the sample according to the particular task in mind. The fourth pillar in the physics AI symbiosis is designing algorithms using physics. Now, traditional computational imaging algorithms are rules-based, handcrafted sequence of operations. Our approach to algorithm development is quite different. It is based on emulating the laws of physics. Phase space transform is one of those algorithms. It performs the best-in-class edge and texture detection in digital images. A second algorithm known as PIVE performs contrast enhancement with record computational speed. And these algorithms are being used in our lab to develop a tool called CytoLive for live cell tracking with applications to drug discovery. Now, the phase stretch transform is a spin-off from our research on time stretch data acquisition, and it basically transforms the image by emulating the propagation of a laser pulse through a dispersive medium. And the dispersive propagation imparts a frequency-dependent phase onto the pulse spectrum, and then the output of the algorithm essentially emulates phase detection as we do in optics. So it basically transforms a continuous one-dimensional physics equation to a two-dimensional discrete equation. And what this algorithm does to the images is quite dramatic. As you can see here with the input image, the output image, and this is the output using the best known edge detection algorithm in practice today. And this phase space transform works exceedingly well, especially in areas of the image where the image quality is low. This algorithm has been quite successful in a number of applications, including as a post-processing algorithm in single molecule imaging, is able to distinguish nearby molecules that are undistinguishable in the original image. A newer physics-inspired algorithms that will be published later this year is called PIVE. It performs contrast enhancement with a quality that is as good or better than the best-in-class algorithms, histogram equalization here and Clay here. But the main point here is that this algorithm has more than 10 times better computational speed. So it's particularly suited for processing large gigapixel images, for example, in pathology or for real-time video processing. Now, I'm going to describe one example of a tool that we're developing based on these algorithms. And this tool is called CytoLive, and it's being developed to accelerate drug discovery. Now, the high cost of drug development is due to the high failure rate of almost 96%, much of it in the early stage. Live cell tracking is a solution to this. It addresses this problem by catching the failure rates at early stage. And it does so by allowing us to understand the underlying biological mechanism of how the cell responds to targeted drugs and which cells do respond and which cells do not respond. Now, observing live cells is very difficult. Cells are mostly water, so they are transparent and they're very difficult to see in the original image. Also, the illumination level for live cell tracking must be kept low to avoid phototoxicity, and this results in faint and noisy images. On the right side, this is the output of CytoLive. Essentially, it applies those two physics-inspired algorithms to this image and is able to very clearly identify the cells, the cell boundaries, and then label the cells and then track them through the live cell video. This movie shows how this tool automatically identifies live cells in the image using those algorithms, assigns tags to them, and follows each cell during its evolution and creates a cell lineage tree, all without manual intervention. Now, in this results shown here, live cells were monitored for 4 days, so the videos extend for 4 days. Manual annotation of the individual cells and creating the cell lineage tree took 30 days. Processing that video using a leading existing tool took 7 hours, and doing the same in CytoLive took a mere minutes. Now, in closing this presentation, I'd like to go back to what we started with. We talked about evolution of science going from empirical to deterministic, and with the emergence of neural networks, back to empirical. There is growing consensus now that bringing physics back into the picture is needed and will pave the path for new applications. We saw several examples of such approaches, neural networks acting as surrogate model for physics equation for fast computations or forward simulations, that is. We saw physics-guided neural networks for improved accuracy, for example, physics regularization. We saw reconfigurable hardware for blending of instruments with AI, optical neural networks, one example. And we saw a couple of other examples of advanced instruments in which the illumination pattern is digitally reconfigurable. And then finally, we saw an approach where physics serves as a blueprint for designing algorithms. We saw one application in live cell tracking, and other applications, for example, to immunotherapy and stem cell classification. On that note, it's been a pleasure to speak to you. Thank you so much for your attention.